In this optimization case study, we're going to be talking about milk pasteurization with heat integration. Now, this is going to be a very common topic for integration of heat to be able to use an incoming cold source or heating also with a cooling on the outlet and be able to integrate that with a cross-current heat exchanger. Now, there's a trade-off here in terms of how big you size the heat exchanger with how much utility costs you have. So for example, from a compressor. So we can run that compressor harder and have smaller heat exchangers, but then you have higher utility costs. And so we want to look over this 6-year time span and be able to minimize the total cost of operating this milk pasteurization process. And you'll see here we have 4 heat exchangers. So we need to size all of those given the constraints about the temperatures. Okay, so we have 4 degrees Celsius coming in for the milk and 7 degrees Celsius coming in, 4 degrees Celsius going out. We need to get the milk up to 73 degrees Celsius. Now we have some cooling water at 30 degrees Celsius and then coming out at 35 degrees Celsius. And we have these different temperatures here. I'm going to call this temperature 1, temperature 2, and then this is going to be temperature E of the expansion valve. Okay, so we have an expansion valve. We have this refrigeration cycle going on here. So this is going to be hot right here. And then we also have, after it evaporates, we have the cold when it comes through this expansion valve right here. That's where it cools off. Okay, so we have this refrigeration cycle right here, and then the milk cycle. The milk cycle, I'll just put that here. The milk cycle that comes through here, through these heat exchangers with the water. Okay, or you have the water that's cooling, but you have some kind of a refrigerant here in this loop. Okay, so we want to optimize all of these heat exchanger areas given all of the economics of it. But it's just going to be a combination of some heat transfer principles. And let's just go ahead and start off with the coefficient of performance. Okay, so the coefficient of performance is going to be equal to, okay, this is the heat transferred from the evaporator, okay, divided by the work of the compressor. So that's going to be the total amount of cooling that takes place and divided by the compressor work. Now, that's like a theoretical Carnot heat pump, and we're going to assume that we're going to be 75% of that efficiency just because of the inefficiencies in the compressor and other things. Also, if we put a total energy balance around this whole system right here where the milk is coming in and out, and then this cooling water is also coming in right here. If we just look at all the inlets and the outlets and perform an energy balance around that, we'll have the work of the compressor plus m dot, the mass flow rate of the milk, all right, times the enthalpy of the milk in, all right, minus the enthalpy of the milk out, and that is going to be equal to the mass flow rate of the water times the enthalpy of the water in minus the enthalpy of the water out. Okay, so there's just an overall energy balance, conservation of energy, and then we can compute some of these terms, such as this one. We're just going to assume that one, we can model it as the mass of flow rate of milk times the heat capacity of milk times the temperature of, I'll put T milk in minus T milk out. Okay, and similar to this one, we're just going to break out the enthalpy into the mass flow rate times the Cp times the delta T. Okay, so we have a heat capacity for water as well. Okay, so let's let's go ahead and just substitute some of these equations in and calculate the work of the compressor is going to be equal to the mass flow rate of milk. I'll say plus the mass flow rate of milk, C sub P milk, and that's going to be T milk in minus T milk out equals the cooling water. Okay, so the cooling water heat exchange. Now, we also have the heat transferred by the evaporator, condensers, and regenerative exchangers can be modeled by Q equals the overall heat transfer coefficient times A times delta T. Now, with these countercurrent heat exchangers, we're going to use a delta T log mean for those. And the delta T in this case is going to be the temperature H2 minus temperature C2 minus temperature H1 minus temperature C1 divided by the natural log of the ratio of TH2 minus TC2 divided by TH1 minus TC1. Okay, so that's the delta T log mean. And so that does a better job of expressing this delta T. Otherwise, you'd have just constant temperatures and it wouldn't really reflect the heat exchanger. Okay, so let's go ahead and do the next one now. We'll have the Q of the expansion, okay, is going to be equal to Q E of the milk. Okay, and that's going to be equal to the mass flow rate of the milk, C sub P of the milk, the heat capacity of the milk, and then we're going to have T2 minus 4. So that's the outlet right there. Okay, just make sure T2 is in Celsius as well. You just want to make sure those units match. Now, we have some data as well. The flow rate of the milk, okay, that's going to be equal to 4 kilograms per second for 4 hours per day. Okay, that's our flow rate. We're going to only operate for 4 hours a day. The specific heat for the milk, the heat capacity, is going to be 3.75. And that's going to be kilojoules per kilogram degrees Celsius. Okay, and then we also have the cost of all the heat exchanger surfaces. So this is going to be the cost of heat exchangers is going to be equal to $200 per square meter. All right, now this is where the economics come into play, where you can have larger heat exchangers and have less utility costs, but then you're going to end up paying for this additional surface area. All right, the overall heat transfer coefficient is going to be 500 watts per meter squared degrees C. All right, that's for the regenerative heat exchanger. All right, and then we have the U values for the evaporator, U value for the fore-condenser, and the U value for the after condenser is going to be equal to a little bit more. Okay, sometimes you have to have thicker plates for the regenerative heat exchanger, so you have maybe less of a heat transfer coefficient. Okay, so these you get a little bit more. All right, and then the cost of the compressor. So this is just the initial capital cost. It's going to be related to the total amount of power that it's rated for. So that's going to be per kilowatt of power. So if you have a larger compressor, you just have to pay more for the compressor. It's going to be a bigger compressor. All right, and then to run the compressor, the cost of electricity is going to be equal to 7 cents per kilowatt hour. All right, and that might be a little bit low by today's standards. If you're California, it might be 25. If you're in other places of the U.S., it's going to be different. If you're close to a nuclear or a hydroelectric plant, it might be 2 to 3 cents. So it just depends on where you are. Okay, the interest rate, that one is going to be 9%. All right, so maybe you have a lower or higher number, you can adjust those and then re-optimize it. It might, if you have a higher interest rate, you might favor putting more into the utility side, for example, instead of the upfront capital cost, because it costs more to invest and build that plant. And then the life of the plant, we're just going to assume 6 years, as we mentioned before. So that's the interest calculations. We're going to go out over 6 years. And then the cooling water, we mentioned it enters at 30 degrees and then leaves at 35 degrees. So let's go ahead and optimize this. I'm going to make this kind of small on the equations, okay, just so we can see all of them here as we go through and build this. Okay, so now we're going to do this in Python. We're going to optimize it. Very first thing we'll need is Gecko for this heat integration problem. Let me move this up just a little bit more so we can see the diagram as well. Okay, there we go. We got most of it in there. All right, so we want to initialize our model, and then this just gives a little bit more about determining the areas of the heat exchanger, the evaporator, condensers, and regenerative exchanger, the size of the compressor, the temperatures, the 4 temperatures, that result in the minimum total cost. So we have some parameters here. Our 0.6. Okay, we're going to put all of these into the same unit, so kilowatt per meter squared degrees Celsius. Here's for the regenerative heat exchanger. We also have the mass flow rate of the milk, okay, the heat capacity of the milk, okay, and heat capacity of the water. Okay, the interest rate in fraction, so from percent to fractional, and then the number of periods is 6, so that's going to be 6 years. All right, there's our inlet temperature for our milk, and there's the outlet temperature for the milk. We have the pasteurization temperature, that's our target temperature we need to get to, 73 degrees Celsius. And then we have our variables. This is the compressor work. So as we have a larger compressor, we're going to pay more for it, and we have that as a variable. We also have the heat exchanger areas. We're going to have the area of our 4 heat exchangers, okay, and we're going to have the lower bound of 1 and an upper bound of 1,000, and just give them an initial guess of 10. And then there's our temperature 1, temperature 2, and then evaporator temperature and condenser temperature as well. All right, there's our total cost, and we give it an initial guess of $100,000. Now we have our evaporator as well, okay, and we also have the regenerative heat exchanger. These are the Q values, the heat transferred. All right, and then we have our fore-condenser as well, and after-condenser. And then here's our temperatures of approach. And I'm going to put those as a lower bound of 0.1. We have some ratios as well. So we're just defining variables right now. We'll have equations that come later that calculate some of these. But I've put some of these ratios just so we avoid negatives in the delta T log mean. So we don't enter an area where it becomes infeasible. Here's our log mean temperature differences. All right, and then we have our coefficient of performance as well. I'll put some intermediates here, the cost of electricity at 4 hours per day. Now, one of the ways you could increase the economics of this is to operate for more hours of the day and process more milk, but we're just going to assume 4 hours per day. Cost over time, the multiplier is about 4.5 instead of 6 because of the interest rate on unspent capital. All right, so here I have my multiplier, okay, and then I have my total here. All right, and then cost of equipment as well. So there is all the costs for the areas times $200 per meter squared, and then $240 times the kilowatt for the compressor. Then I'll convert these into Kelvin as well. So the evaporator and condenser, I'm going to need those in Kelvin for another part of the calculation. So I'm just going to add 273. It should be 273.15, but it's close enough there. Okay, here's my total cost. Okay, so there's my electric total plus my equipment total. It goes into my total cost. And then I have the overall energy balance on the regenerative heat exchanger. Okay, so I can cancel out some of the terms for those. And so just the sum of the T1 and T2 equals TP plus TI. Now I'll have my log mean temperature difference. I could make a function for that, or I can just write them out here. So I'm just going to write them out here. Okay, producing some equations for each of those. So you can see each of these are coming into this equation section function right here. Okay, so for each of my, okay, then I have approach temperatures as well as ratios. Okay, and then I'm going to put in the log mean temperature difference. Now for this one, instead of using log mean temperature difference, I'm just going to use the delta T for it. Okay, and you could also uncomment that and then comment that one to use one or the other. So these are just average temperature differences versus a log mean temperature difference. Okay, coefficient of performance, this is 0.75 of the theoretical performance. This is the work to compressor, and then the heat transferred to each heat exchanger. Okay, so I'm going to put in the Q equations. All right, and then that ends my equations. So I've filled out all of my equations now for this problem. And then the final thing I want to do is minimize the cost total. All right, and I'll select solver equals 1. This is the APOP solver. I mode 3, that's an optimization mode for Gecko, and then I'll solve it. Let's go ahead and print the minimum cost as the final solution. Okay, so now what we want to do is go ahead and run this. And I'm just going to run this with IDLE, but you could run it in Jupyter Notebook or from a command line as well. Okay, so this one is going to, it's a little slow on the startup here. Oh, it couldn't make a connection. I don't know what's going on there. I'm going to go with just change directory to desktop. And then I'm going to do Python, and this is heat.py. Okay, so there's my minimum cost right there. That's cost of electricity plus the cost of all the capital equipment. It's about $98,000 to build and operate this for a period of 6 years. Now, we haven't really put in here any of the profitability of how much we can make off of that, but this would be the total cost given the minimized areas and all the other decision variables for our model. And you could add those as well. So let's say we wanted to print as well here all of the areas. Okay, so I'll do AE.value. Okay, and let's go ahead and do this for the other areas as well. And AC. Okay, so if I run this again, then it'll print out the areas for those heat exchangers. You can see none of them are really at bounds. You can see some of them are going to be much more expensive than others. Okay, the 186 meters squared, so quite a large heat exchanger there. And then you could also print out, the other one was the compressor. So that's going to be the compressor work. Let's just look at the W value as well for the compressor. All right, I'll run it one more time. So this is going to be the size of the compressor. It's going to be a 70 kilowatt compressor. So it was able to optimize all of these. Now let's say I said, well, there really isn't that size of compressor available, what I'm going to do is just put this in as a parameter and say maybe I only have a 60 kilowatt compressor available. So this is going to make the heat exchangers larger. And let's just see, from $98,000. Let's see how much more the system is going to cost us if we do not have that as a variable. All right, so 98,754, and you can see it's going to cost us a few $1,000 more, 100,341, because we had to specify that our compressor was 60 instead of letting it optimize it and get it to be a higher compressor. So overall, this is you can change some of these. Like let's say you want to put in a bound, and you say, well, 226 is just a little bit too high. I'm going to put an upper bound of 200 in here. So let's optimize this again and see what that does to our total cost. So you could see that's going to cost you an extra $5,000 for the cost. So for each of these, you can add constraints. You can take away those degrees of freedom from the optimizer and see the total effect on the economics of the process. I hope you've enjoyed this tutorial. There's additional tutorials that are on the course website. So I'll just bring that up. ME 575 is the optimization course, and this one is here under heat integration. And there is a full heat pump assignment, which gives a PDF file with all of this information, along with a diagram. And if you want to get the source code for this as well, just come down here to the bottom and select Get Code, and then copy that into one of your scripts or into your Jupyter notebook. Hope you've enjoyed this tutorial.